Orbital ATK, the company responsible for the solid rocket boosters on NASA's upcoming Space Launch System, completed its final qualification test, QM2. SpaceFlight Insider, with the help of former NASA astronaut and Propulsion System Division Manager for Orbital ATK Charlie Precourt, got a tour around the Utah test facilities ahead of the static test fire.
In a few days, Orbital ATK is going to be lighting this huge, quote-unquote, candle, the QM2 5-segment solid rocket booster. Give our viewers an idea of, they see it on TV, but what are they actually looking at? Give us some of the specifics.
Sure, as like a lot of launches you see on TV, you can't appreciate the magnitude of it unless you're right up close to it. The booster's about 150 feet long. It has over 1 million pounds of propellant in it, and when we ignite it, it will produce nearly 3.6 million pounds of thrust. 3.6 million pounds of thrust, and that's out of one booster, and of course on SLS we'll have 2 of them. It's an immense amount of power that we're harnessing here. And the temperatures that we see inside the motor when the gases are burned or when the gases are formed from the burning propellant are well over 5,000 degrees. Some propellants burn as high as 6,000 degrees.
So the inside of this will actually on test day reach 5,000 degrees.
Exactly.
Maybe as high as 6?
Exactly, yeah.
Now, we're sitting in T97, your testing bay, and it's cold in here. We've been outside in Utah, and for this time of year, Utah is not cold. So can you talk a bit about why you guys have it so cold in here and the process of getting it to the right temperature?
Sure. The important parts of a solid rocket motor are the ability to control what we call the chemistry of the propellant. And the way it burns, as we just talked about, to create all that thrust, the temperature of the propellant itself has an effect on the performance that you get out of the propellant. So what we do is we test the extremes of the temperature ranges that we might expect to see on a launch day out of Florida. And in this case, we want to test around 40 degrees. The actual parameter limits we're targeting for test day, 38 degrees to 45 degrees. We're targeting 40, 41, so we're well within that band for the data that NASA wants. What we're talking about there is what's called propellant bulk mean temperature, PBMT, which is the average of the entire over 1 million pounds of propellant. So we have sensor probes inside below the case wall that are measuring those temperatures, and we integrate all of those readings to make sure that that temperature is within that target range. This building has been chilled for over a month now, because you can imagine you don't just chill it overnight and expect 1 million pounds of propellant that otherwise is at 60 degrees to come all the way to 40. Right. So we've got it down there, and we've been holding it there for a week or more now, actually close to 2 weeks by this time. We're just stabilized holding it there, and about 6 hours prior to the ignition, we'll roll the building forward. This whole building is on a railway, and it just rolls forward to the front end of the test bay, exposing the booster for the test itself.
They did fly in shuttle, but shuttle used 4-segment, and SLS is going to use 5-segment.
Correct.
So there's got to be some similarities, and there's some dissimilarities there. Can you share some?
There's actually a lot of dissimilarities. So the case hardware is a fairly simple structure, but what's on the inside is what's important. So I mentioned in the developmental tests that we had taken some of the insulation out. We actually also changed the type of insulation we were using. It's been modernized. And so each of these boosters is well over 1,000 pounds lighter than the shuttle boosters from a insulation standpoint. The chemistry of the propellant is a little bit different, and the quality, if you will, of the manufacturing process is far greater. We have taken 47% of the flow time out of building these boosters from what we used to do in shuttle. So the manufacturing processes that people don't see are really the advances that we're making in technology. Much higher degree of quality control. We can actually now, through non-destructive inspections, see 100% of the interior of each segment and know exactly what we got when we go fly it. So there's very, very high quality on the quality control.
SpaceFlight Insider also got to go underneath the booster, where a dry run of the test fire was underway, as Orbital ATK has been doing for up to 3 weeks before the QM2 test.
Dry runs, it depends on how things are going, but they'll run this several more times, and they'll actually probably do one on test day. And it's just a matter of everybody getting comfortable and running through this and trying to find things before the actual test that need to be tweaked. We've been in cool down on the motor for several weeks now, I think, right? And so we've achieved a 40-degree bulk temperature in the building that's above us that houses the motor, but we're constantly doing the final preparations that enable these practice runs.
Booted up and suited up once again, we asked what was next after this final test.
So QM2 is a qualification, so we had 3 DMs, as you said, developmental motors, where in each one we changed some things incrementally to get to a final design. For example, there is insulation just on the other side of the steel case. There's a specialized rubber insulation before you actually get to the propellant, and that insulation is intended to protect from those high temperatures so that they don't reach the steel walls of the case. The amount of that insulation we incrementally reduce till we optimize so we don't carry more weight than we need. That was one of the things we did during the developmental test. Then we finalize the design, and then we take it through 2 qualifications to show at a warm temperature day, which we did last year, and a cold temperature day. Now we bracket the data that we need to know how the motor will perform on any given day in its operation. So qualification number 2 means that we're done qualifying and we're ready to go fly EM1, Exploration Mission 1, in 2018 with Orion on its first integrated flight, unmanned, out around the moon and back, and then it'll be ready for crew. So we're already building the booster for EM1.
3, 2, 1, fire! +5.
Head in CO2. Activate. Quench tool command forward and aft CO2.
Activated. T plus 145 seconds.
Had a cow drift up, wander up there.
A cow.
A cow wandered up above the test stand and fell down the side of the hill. And by all rights, shouldn't have been able to get up. I got up and walked away. Amazing. Amazing.
Not during like a test or anything.
Well, I was getting ready for one, but you see that rocky area up there?
Oh yeah, I know the one you're talking about. Yeah.
Yeah. So as we get up on you'll see how vertical it is up there. He was up on that ledge where the grass is above the open cut in the sand.
And
he just tumbled down the side of the hill.
Did you guys get it on video?
Yes. Yeah. It was like, what are we going to do about this cow? And then next thing you know, it took care of itself.